Alright, welcome back to Pointers in Memory. Let's finish up these slides today. So down here we go. Let us first remember some syntax. So here are two questions for you, number 1 and number 2. Do them both, please. So if I use a star in the type of a variable, what does that mean? So I say something like, let me get a pen, int star p. What does that mean? And then if I use a star somewhere other than a type, like, I don't know, star p equals star p plus 1, what does the star mean there? Because it's an overloaded term, right? Used in different places, it means different things. So what is 1? Give that a try. That means we make a pointer. This is the type. It modifies the int. And it says that p is a pointer to an integer. So that's what that one is. So the first question is A. And then if you use a star somewhere other than a type, which of these are you getting? You are going to get, if you think about it long enough, you're going to get the thing that that pointer is pointing to, and it's like you're following it, and that is called a dereference. Okay? So that one is C. Hopefully those terms are coming back to us and they make sense. Address of is none of the above questions. Address of is something like, you do this. It's how you initialize a pointer. You say int star p equals the address of x. That's how you get the location in memory where some other variable lives. Okay? But once you have that set up, then you want to dereference and follow that pointer to that location. Okay? So that is that. That is pointers. And pointers are very useful in this thing called the heap. Okay? So let's talk about it. It's a new term. Remember how I told you that we have global variables and those could live forever? Those are nice things to have sometimes when you want a variable that can be accessed everywhere, that lives for the life of the program. That's quite nice to have. So let's think about that. I'll give you an example of that really quick. And then I'll talk about a new option. Okay, so let's remember global variables quickly. I guess I can just do it here on the side. So a global variable is just anything defined outside of a function. So here's like a main function, and here is the space above main. You can start making variables, right? And you can make a giant array of a giant size. You can make a single int, right? Int global equals 42. And the idea is these variables, they live forever. They can be used in any function, including main, okay? The fancy term for that is variables are created, they're allocated, space is made for them. Right when the program begins. So as the program starts, all the global variables get space and memory made for them. They get allocated, we say, and they live for as long as the program ends. Even if you're done with this giant array halfway through the program, it lives forever, okay? And that is their downside, right? We don't like sometimes that a lot of memory sticks around until the end of the program, even though we needed it between a bunch of functions for like the first half of the program. That's unfortunate. So yeah, maybe you only needed that huge array R for part of the program. It's a huge waste of space to make it a global because you could have used that extra memory maybe in the second half. Okay? So there's a new way. There's a new way to get things that live forever, and it kind of ties in with pointers, as we'll see. It's called the heap. Okay? Let us go there. So before we get there, let me show you like why global variables live forever. Here is what a program looks like when we run it and it gets made in memory. Let me show this to you. So this is exactly how, essentially, simplified, this is a form of what the memory looks like when you start a program. Okay? This is how memory is arranged within your program. There are a bunch of different spaces called text, globals, heap, and stack. Okay? So let me talk to you about all of those new terms. So the text part of your program, like this, these are all the different memory places in your program. This is your entire program. And it like spans a bunch of addresses, like you start at 0 and you go to the highest address. That is what your program thinks it owns, all that kind of stuff. And then the text part is the code. You don't think about it, but your code, the thing that your CPU is running to execute your program, like your main function, it needs to exist in memory too, right? There is some way to encode instructions that, hey, I want to return 0, hey, I want to add 1 to this variable. Code goes in memory too. It's called the text section of your program. And because you don't ever want to change your code as it's running, it's a read-only section, we say. Okay? So that's that one. And then there is another place in memory just for the global variables, since they live forever, so that we get a global data space for your variables. So you can have your little global variable, you can have your giant array. Those live here, and that size never changes. Like, they get that memory at the beginning, and they keep it forever. And then we have another part of the program that we already know about, right? We have the function call stack. So that is where all your local variables live, like main starts off the program at the bottom of the stack, and then once you call functions like foo, it gets called, it adds space to the stack, bar gets called maybe, it makes room on the stack for it, and all of their local variables, right? That's where all of those live, in their stack frames. And so that takes up a bit of this third portion of memory. This is just one big piece shared by two people, okay? And we say that the stack grows downward, so kind of my diagram should maybe be flipped. Stack grows towards lower addresses, we say, okay? Looks kind of backwards, but at least this is the way that I've been drawing it in class, so we're good. And the stack fights with this other portion of memory that is new for today called the heap, okay? And the heap grows upwards towards higher addresses. And what it does is it holds something called dynamically allocated data, memory that you want to make on the fly and have last for as long as you would like. So we'll get into that on the next slide, don't worry. But what I'd like to tell you is the heap and the stack, they share that third portion of memory, okay? The stack grows down and the heap grows up. And if they ever meet each other, that means you've run out of memory in your program, okay? And you'll get a runtime error, which is kind of cool. But that's what it means to run out of memory. Like, you've called too many functions or you've made too many dynamic variables, okay? The heap is all about dynamism. So I can make a variable that lasts for as long as I ask it to, and I can make it go away. That's what the heap means in a nutshell. I will explain more on the next slide. But that is your intro. This is what a program looks like. This is how it's arranged in memory. It's got some stuff that can never change, and some stuff that keeps changing, like all the functions being called, and all the things that we are dynamically allocating on this thing called the heap. All right, so let's go more in depth into that. Let's talk about what the heap is. All right, let's figure this out. So the heap is all about creating and destroying memory. You have that ability now with the heap, only when you want, okay? So it's kind of like global variables, but better, because heap memory, you can make it live forever if you'd like, but you can also get rid of it whenever you want to, okay? Like globals, heap memory can potentially live forever, and unlike globals, though, you can get rid of stuff. Any memory that you make on this thing called the heap can be removed whenever you would like, so that's the beauty of this, okay? And I will draw a diagram in just a second, but here's one nice example of why you might want to use the heap. You don't have to say up front before the program starts how many things you want to store in it. You can, on the fly, as your program changes, store new things, make new space. So maybe you had like an n variable that the user enters, right? That tells you how big of an array you need, like how many things that the user is going to type into you. So maybe like it could be 100, it could be 10, it could be 1,000, it could be 10,000. We don't care. We can use the heap to make a array of that size later. Isn't that beautiful? And it just like comes out of thin air. That can be our array now. We can make it on this thing called the heap, and we can work with it, do fancy stuff, and then get rid of it once we're done. All right, that's the goal. And I've been hyping it up enough. Let me get into what it really is. Let's talk about this heap. All right, let's figure out how to make stuff on the heap. There is a new operator, and its name is new. So let's talk about it, okay? What it does is it returns a pointer to some type you give that has been made on the heap. Okay, so let me show this to you. You can say new, that's a new keyword, and then after the word new in C++, you can give a type name. And that goes and tells C++ to go make something of this type, an int, on the heap, make space for it please, and then it tells you, like the result of this is it it's telling you where it got made. It's telling you the address where that new memory got made, so it gives you back the pointer to the start of that place. Okay? So new int, if you say that, it gives you a pointer to a new integer that gets allocated on the heap. Okay? So here's how you might use that, because new int gives you back where it got made. It gives you back that pointer. You can assign that to a local variable, and now you have an int on the heap that you can use. All right, so let me show you what's going on here. So here's like your stack where your local variables live, and here's the heap. This line makes a local variable called n that lives on the stack. Maybe this is a main or something. And new int makes a new place on the heap, all shiny and new. Brand new memory just got made for us. Beautiful. And it has an address. Maybe the address is 100. And of course it's initialized to garbage stuff. But new int gives back the address of where that thing got made. So it gives back the 100. And we can put that into a pointer called n. So this is how we can access things on the heap. We can't give them names, but we have addresses that point to them. Okay? So that sets up this. And this box lives for the life of the program until you tell it otherwise. Okay? And you can set it. You can be like, all right, star n equals 42. Use it like any other end pointer. And so now this box holds 42. But this memory lives longer than this function call will live. It lives potentially forever. Okay? So let me show you that in code. Let's go. So this is the heap. So int star n equals new int. All right, so new int, we can say returns. It's kind of like a function call. Returns a pointer to a brand new integer on the heap. It lives for as long as we'd like it to. And let's see here. Then you could use it, star n equals 42, and you can see out it just like that. And it lives longer than things on the stack, so let me prove that to you in just a second. Yay, so it gets 42, and let me do something cool here. Let me show this to you. So like, let's make a function that returns a pointer. Make new int on heap, for example. And let's do this. Let's put the n here, and I don't know, int star p down here or something. And let's call make new int on heap. Let's have this return n, just to prove that this place on the heap is not going away. It is still accessible, it's still valid. And let's get that pointer down here and set it. How cool is that? So n is a local variable. N itself is a local variable, but the thing it points to is on the heap. It lives forever until we tell it otherwise. When this function returns. All local variables go away when the function returns, but heap stuff, just like global variables, does not. So I am allowed to return that pointer, put it somewhere else, set it, and use it again. Isn't that neat? So again, I have 42. So that is the heap in a nutshell. That is the new operator. That's how you make something brand new on the heap. Now let me talk to you about how to get rid of stuff on the heap. You can use the delete operator. You give it an address, because that's how you associate stuff on the heap. That's how you talk about it. You say delete, and then a pointer to something, and then it deletes that memory. How cool is that? So you use delete once you're done with something that you made on the heap, and it will get rid of that memory. It will reclaim it so that maybe you can reuse it later when you make new stuff. Okay? So let me show you what that means. If you use delete, this is essentially what happens. You can do it like this. You say delete n, where n is a pointer to something on the heap. All it does is it goes to that place in memory, address 100 that n was holding, and gets rid of that memory. Now it is no longer allocated. And now you have to be very careful. You can't use n anymore. That address does not belong to you anymore. I hope that makes sense. Okay? So maybe you want to set n to like null pointer or something special to make sure you don't accidentally use it. Excuse me. So that's how the delete operator works, and let me just show that to you here. So now that I'm done with this memory, with the heap memory, I can delete it. So even though it got made up here in n, I returned it. Now I'm calling that address p. Delete p goes and deletes that memory from the heap. Yay. So it's still going to work, just we told that int that we were done with it and that we didn't need it anymore. And so that saved room because maybe we had more stuff down here that needed extra memory. Now we could have used that extra memory. Okay, so that's what the delete operator does, and it's quite useful. All right. I'm about to talk about arrays because those are important things that we might want to make on the heap. Let me teach you some interesting facts about arrays. So arrays, believe it or not, are secretly just pointers. This syntax looks a bit weird, but it's secretly just making place in memory that is 42 ints long, and then it's giving back a pointer to the start of it. Crazy. So this syntax is really making stuff involving pointers. And R, if you say R just by itself, it's really just a pointer to the start of that array. So let me show this to you. So if you say int R42, it definitely makes 42 ints in memory, totally. But R, even though I usually write it like this, right? But really what's going on is, let's say that the first int is address 100. R by itself, it's really just a pointer holding 100, the address of the start of the array. That is the secret. So let me show that to you. Maybe I want to make a new file. So here's a size 42 array of ints. Let me see out R by itself. Or you know what, let me make an array of things that I actually know what are inside, not undefined things. So that's R. It holds 5, 6, 7, and here is me printing out R by itself. I'm just saying the name R, not like R of 1 or R of 0. Just the name R. What does that look like? That is a pointer, and it's a pointer to the start. It's a pointer to the start of the array. Which means, what do you think is going to happen when I print star R? Follow that pointer. Well, if it's a pointer to the start of the array, the first thing in it, it's going to go to that first thing, printing 5. That's the first element in R. Interesting, right? We wouldn't have thought of that, but that's really what's happening. So that brings us to something called pointer arithmetic, okay? And it gets a bit weird looking, but I promise it will make sense. So you can add numbers to pointers. You totally can. Just like I said, star R, I could have added 1 to R and dereferenced that. It would get the next thing in the array. So here's my array, R, and let's say that it lives at addresses 4, 8, and 12. Those are my 5, 6, and 7 ints. If I say R plus 1, that goes to this box. It gets me this address. It goes to the next place in the array, okay? And the reason this works is because R, when you say R by itself, it's the starting address of the array, and 1 is like an offset, okay? Even though R plus 1 you'd think would be 5, right? If the first thing in the array starts at address 4, you think that R plus 1 is 5, but C++ is smarter than that. It knows that I want the address of 1 int later, not 1 byte later, because R itself is a pointer to an int. We want the next one, please. So saying r plus 1 gets you this 8, and dereferencing it gets you this 6. And so secretly, whenever you use this normal syntax that I've taught you before, it's really being translated into pointer arithmetic, so adding to the starting address of an array, and dereferencing it. What? How crazy is that? So that is what's going on here. So cout array of 1, that is equivalent to array plus 1 dereferenced. So go one int after the start, dereference it please. That's called pointer arithmetic, and so it's going to print the 6 both times. These are equivalent lines or equivalent pieces of code. This is really being translated into a use of pointers. How fun. So you can also do this for C strings, because what are C strings but special char arrays, right? And now you finally know that because you can treat arrays as pointers, just like this, now you know why everybody says char star instead of char bracket bracket. They're equivalent types. That's why it's char star. argv, bracket bracket. This just means an array of characters, because what is an array but a pointer to the start of it? You see that? That's how that works. So, yeah. Similarly, let me just prove that to you. C++ is capable of treating any pointer like an array. Hopefully it really was pointing to an array, but you can totally do this. Int star p equals r, right? Because r by itself is a pointer to the first int. Now I can do this. I can use array-like syntax on p. Instead of r2, I can say p2. It's just a pointer. But that syntax still works. It treats it like an array. Go 2 ints later, past the start. And it really does give the 7 back. All right, so arrays are secretly pointers to their first element, and we're moving around them using this thing called pointer arithmetic. Hopefully that was not too confusing. I know that's a weird thing, though. All right, so let's keep on trucking. Let's talk about new and delete for arrays now, because those are important things. Sometimes we want to make a bunch of memory at once, and the heap is perfect for that. Okay, it's for allocating and deleting arrays as well. So let's do that. So new always gives you back a pointer to the start. So if I want an array of ints, I'm going to get back a pointer to the start of it. That's fine. And if I want an array of 42 ints, I just put some brackets after new int. Okay, that makes an array of ints on the heap of size 42. So if I were to run that line, here's what would happen. Stack heap p is a local variable. It gets set to the starting address of this big long array, maybe 100. That's my favorite name of an address. And so it's pointing here. That's what that syntax will do. Makes a brand new array on the heap. Fun. So that is that. And then now you can use this array. You can use p just like a normal array. You can say p of 0 equals 42, because this syntax still will let you use this array syntax. All right, even saying that it's a pointer, it will let you use array stuff, array operations. Okay, and p just holds the starting address of that array, and you can move around it as normal, and you can fill it 42, 43, whatever. And once you're done with the thing on the heap, you say delete. But because C++ needs to know, like, hey, was this pointer just a single int on the heap, or was it an array of things on the heap? Do I need to delete more than just one int? You have to tell it, oh, this was an array that we allocated. Please delete the whole thing. So you say delete bracket bracket instead of just delete, and then you give the starting address. So delete bracket bracket will get rid of that array, and that will do it. All right, so let me show you that quickly. So making an array on the heap. So you say int star, I don't know, q, new int of size, whatever you want, 42. So that makes an array of size 42. You can set it, like Q of 5 is 55, and you could use it as you'd like. And then once you're done with the array, you say delete, bracket, bracket, and that gets rid of it. You give the pointer to the start of it, as usual. And so it's going to work like that. So that makes an array of size 42 on the heap. And Q is the starting address of it. Okay? So that is new and delete for arrays. And now I have a question for you. Fancy stuff is involved. So look at this code. Think about what's going to happen. I would like you to draw the state of memory after those lines have been run. All right? And definitely section off the stack from the heap like I've been doing, like this. Okay? So tell me what things are on the stack, what things are on the heap, what things hold what addresses. You can make up numbers if you'd like, but definitely draw the arrows. All right? So that's step one. And then I want you to draw what happens when you say delete P as well. Okay? So give that a try, both of those questions, and then I'll show you my answer. All right. So this line makes a new variable called P. That is a stack variable. It's a local variable, right? Makes something on the stack. Here's the stack, here's the heap. So P is a new int star. Okay, so P holds the address. It just made a box in memory, but this box holds int stars. Crazy. So that means we need a pointer to an int. We need a pointer to an int star. It's making space on the heap for an int star, and it's giving us the address of that int star. So this is space for an int star. And P holds that address. So maybe this was 100. This is pointing there, just like that. Okay? And then I can go and I can do this. Star P, that's this box, right? It's capable of holding, remember its type. It is an int star, right here. And this one is an int star star. This one right here is capable of holding the address of any int, right? And we can make one of those on the heap. We can say new int, that gives back the address of a brand new integer on the heap. So that makes a new box right here. Maybe this is address 200. And this one will hold that and point to it. You see that? So star P, that's setting this box to a brand new integer, and it's capable of doing that because this box is an int star. And so it holds the address of this box. That is just a single int, okay? That's the type of this one on the heap. And then, look what happens here, star P. So star P is this one. Another star goes here and works on that box. Worries about setting it to 42. That's what happened. But I just made up address names, but the arrows and the contents of that last box are always like that, okay? So that's this diagram. Do you see where the stack ends and the heap begins? Everything made with new lives on the heap. Any local variables defined like this with a type name, they live on the stack. Okay, so that's what happens first. And then when we say delete P, what goes away? Definitely not anything on the stack ever goes away. It's only heap stuff. Is it both of these? Is it this one? Or is it this one? And just going back to these ideas, you say delete. It goes to that thing, goes to that place, that address, and deletes it. Just that thing only, okay? So if you say delete P, that says, okay, P is address 100. It goes right here and deletes that one. Only this box, okay? So we kind of lost a way of getting to this one, to this int. We can never use it again. We lost the address of it because it was held in something that's been deleted now. But that is what's going on in memory. And so this is where I want you to become comfortable. Okay, this is where I want to get you with these slides and the book and your future labs and things. Okay, this is where I want you to be in terms of pointers and understanding them. All right, so there is a term for losing this. We just lost access to this box on the heap, right? Because we can't go through this deleted memory anymore. The term for that is called a memory leak. We have just leaked memory, okay? A memory leak is when you lose access to data, and that data just sticks around forever. That memory can never get reclaimed because you don't know where it is anymore. You don't have an address. Like, you forgot its address. So let me show that to you. So here is a line that makes a brand new int on the heap. So stack heap. And so that is I, a box called I. It is a pointer to an int, and that int just got made shiny and new on the heap. Maybe it's address 100. So I will hold address 100. And so that's all nice. Shiny new int on the heap. That was the first line. Then we can set it, of course, set it to 42, sure. And then I can do this. I can say, oh, you are now the address of a brand new int that I made on the heap. This one over here. Maybe that's address 200 now. And oh man, shiny a new box over here. Now what is I doing? It's pointing, like it now holds 200, right? It's pointing to this box. That is what it's doing. And then you could set that to 43. But yeah, you lost this one. That no longer points in that direction. We're now holding this address, the address of this box down here. We have no way of getting back to this one. We forgot, like we overwrote the one place that we had that told us where that first box was. We lost access to our first int. That is called a memory leak, okay? Which is very unfortunate. We don't like memory leaks. But that is what can happen. We just lost access to that place in memory, okay? Sad day. So don't ever do that. Don't leak memory. Always delete it first. You should have maybe in between these lines called delete on I, because then that would get rid of this one, and then you can maybe reuse that memory later. Okay? So that is a memory leak. And I think we're ready for like an in-depth example. Let's do something that you might want to do using the heap. So we'll ask the user for like a number, and then we'll make an array of that size on the heap to hold those n things. Then we'll ask the user for those n things. Hey, what do you want to store? We'll put them in the array, and then maybe we'll calculate the sum of that array. How does that sound? And then we can delete it once we're done with all that. Okay? So that sounds like a plan to me. So let's do like, I don't know, sumarray.cpp. And this array will live on the heap. So enter the size, we'll get it into our local variable called n, and then we can make a heap array of size n. And that will live as long as we ask it to, and no longer. All right, so let's do this. Let's be like, I don't know, we could say, let's just call it r as usual. So new int of size n this time, and so it's an arbitrary size, whatever the user gave us. We can't think ahead of time what it could have been. We don't have to care about that. And then we want to fill it. So for int I is 0, I is less than n, I plus plus, cout, enter the next element. And so we'll get it, and then we'll put that element into r of I. Yeah? And so now we have a filled array, and now let's do stuff with it. We can sum it together, sum the array. We can use it now. So like for int I is 0, again, I is less than n, I plus plus. We'll start out our sum variable at 0, and then we can be like, just as usual, use it as a normal array, because it really is. Sum, add into it r of I, and then output the sum. Okay, and now we've done all the work. Actually, before this line, we've done all the work with r that we need to do. So we can delete r now. We can delete r. Now we're done using it. The rest of the program doesn't use r anymore. We just filled sum based on r. So that will allow us to delete. Remember, because it's array, it's delete bracket bracket r. Okay, so that is the program. So enter the size 3, enter the next element, so 5, 6, 7, and oh, oops, did I do it too many times accidentally? Uh-oh, it looks like I did something wrong. Let's figure out what I did wrong. size 3, we got an element, we see it, oh, C into N, excuse me, it should have been C into element. I don't want to overwrite N because that changes how this for loop executes. We don't like that. So that is a very common error that you just saw me commit. Excuse me. So let's do it now. 5, 6, 7. So now the loop's going to go the correct amount of times. And 18 looks about right. All right, so we're using that array. And then once we're done with it, we don't need it anymore. We can delete it off the heap. And that will give us room to make newer, bigger things later so that we don't run out of memory. So yeah, usually you do this not all inside of main, but this is one example of using the heap to do something non-trivial. Okay? Hopefully that made sense to you. And now it's time for me to tell you a secret. Vectors that you've been using, strings that you've been using, deep down in their underlying implementation, like their member variables, they're secretly using dynamically allocated arrays. What is a vector but an array that can change its size? So it just keeps on, well, I need a bigger array, let me delete this one and make a bigger one. That's what it's doing secretly. A vector is, the underlying representation of a vector is a dynamically allocated array on the heap. And same with a string. Like you add two strings together, it takes those characters, which are arrays of characters made on the heap, and it makes a bigger array, deletes the old ones. That's what's happening. So you've secretly been using the heap this whole time and you haven't known about it. All right? How cool is that? So I have two last topics. This one I'm not going to test you on, but this one will be useful. I still won't test you on it though. I promise that this last one will be extra useful. But let me give you a even more in-depth example of when you're going to want to use pointers, right? Because I already told you about references, and those kind of like make it easier to do pointer-like things without like blowing up your program. Let me show you a good reason to use pointers and the heap at the same time. It's something called a linked list. All right? Let me show this to you. This is a super brief intro. I'm not going to go very far into them. Okay, your book talks about them a little bit. Definitely read about them. But this is a CSCI 41 topic. Okay, you're going to get to know them in depth there. So we'll just save that for you then. What a linked list is it's a data structure that consists of, what in the world? It consists of a bunch of things called nodes, and those hold data and also a pointer to the next node in a list. All right, so it's like a list of things, and they're chained using pointers. All right, and all the time, almost always, you make these things called nodes on the heap. All right, and let me try and draw them for you. So a linked list is a competitor to arrays and vectors because some things are much easier to do with them. All right. And I'll just do this in diagram form. We can wait till CSCI 41 to actually code this up. So here's an array. You know what's really hard in an array? Maybe I have like room, like I have a size 4 array. It's really hard to add something to the beginning and then like I want to add 0 to the front and keep the rest of these. Then I'd have to like shift them all over, right? That sucks. Or maybe I only have a size 4 array, but I really notice now that I need 5 elements. You cannot add a new element to an array, right? That's impossible. So there are some things that you can't do with arrays. Same with vectors, all right? Linked lists, though, they look like this. There's like a pointer to the first node, and the rest of the nodes live on the heap. And so here's what a 1, 2, 3 list would be drawn like. It holds data and then a pointer to the next node, so a bunch of nodes look like this. Here's a 1 node, a 2 node, and a 3 node. And they all know where the next one is. That is 1, 2, 3 in a linked list. And then this one's like, there's nowhere to go. I'm the end. That's what a linked list looks like in memory. It's got data and then a pointer to the next node. And look at what is super easy to do. I can add a new node wherever I would like to. I can add a new node in the beginning, in the end. I can change the size. I can add stuff in the middle without having to like swap around things. Let me show that to you. And then hopefully you will be excited to learn about them in CSCI 41. Okay? I'm not going to test you on these in this class. But let me show this to you. So on the stack, let me draw this out a bit more. And here's the heap. On the stack, here is our linked list. We had a pointer to the start of it. and here was all the nodes that lived on the heap. It was the list 1, 2, 3 in that order. I can make something and put it at the beginning by doing this. Just make a brand new node, call it 0 on the heap, have it point to the original first element, and then just change this. Hey, that's the start of the list now. I didn't have to shuffle anybody. I just had to do a new operation, make something brand new on the heap. I had to set this pointer to something that already existed. It was already an L. And then I had to change L to be a pointer to that first new element. And so I think you can imagine if you had a giant array, what you would have had to do, right? This was 1, 2, 3, question mark. You would have had to shift everybody. If it was a size 1,000,000 array, you would have had to shift 1,000,000 people. And then you could put the 0 where it needs to go. That's something nice. This is only like 3 lines of code. Very fast to do, to use linked lists like that. So that is my quick introduction to linked lists. I promise they're useful. Hopefully you can kind of see how they are. And that is all that I want to go into them right now, though. Definitely read about them in your book if you're interested, and I'd be happy to talk about them in office hours. But the last concept I want to talk about today is this thing called GDB. It stands for the GNU Debugger, and it helps you debug your code. It's a program where you can run your programs, okay? And it will help you discover errors. So let me teach this to you now, GDB. All right, so yeah, GDB stands for the GNU Debugger. Those are the same people who made G++. Stands for the GNU C++ compiler, right? And this is a program where you will run your own programs. It's a program that runs programs, and it will tell you about that program as it's running, okay? It can remember things and print out, for example, the values of your variables, the line numbers where a runtime error happens, etc., etc. Very, very useful information, I promise. So in order to have access to GDB, it exists, to be able to use it properly and have all this interesting, nice information, all you have to remember is to compile with an extra flag. You say -G in addition to everything else, and that adds debugger information to your program as it's compiled. So you're going to say G++ standard equals C++ 17, and then you add a -G here, just in addition to this guy. And then you compile whatever you need to compile. See, foo.cpp-o-foo. That's all you have to do, and that -G gives you that debugging information and allows us to open up GDB and use it to its fullest. So let me just make a sample file called segfault.cpp. We're going to have a segfault happening, and it's going to tell us, GDB will tell us where that segfault occurs. So let's make it not obvious. Let's make a function called let's call that, and it's going to be like int star p equals null pointer cout star p. Yeah, that sounds like a good segfault to me. So let's compile that, and what I'm going to do is I'm going to compile it with a -G as well as everything else. Boop. There it goes. Of course it segfaults when I run it. Very nice. But let me show you something else. So here's the program up here. Let me open it up in GDB. So instead of saying /segfault, you say all that, but you put GDB at the front. It's a program that runs your program. So you say GDB./segfault. Just like that. Hit enter, and it plops you into GDB. If your terminal is small like mine, you have to press enter to get the prompt. But this is the GDB prompt. We're not in the terminal anymore. It's ready to run our program that we compiled with debugging symbols. So yeah, in order to run the program, you can say R for run. That's a command to GDB. So R for run, hit enter. It's like starting program, and look at this. It stops, and it says, oh, segmentation fault, and it tells you the file, it tells you the line number where it happened, and it even prints out the line number where it happened. It's like, oh, okay, line 6, you had a seg fault there. Hopefully that's helpful. Isn't that amazing? You get to see exactly what happened there. And you can see how you got there. You can say BT stands for backtrace to view the stack, to see all the function calls that were taking place in order to get to this point in the program. It's a simple one for us, at least. Main starts the program, then calls uh-oh, and we were inside of uh-oh when things went wrong. So that's the stack. You see it? It's drawing the stack for us, and the error happened inside of the uh-oh function, it says. So if you think that's cool, let me show you this. You can print the values of the variables. You say print space, the name of the variable. That's a command to GDB. That prints the value of the variable in your current stack frame. So I'm sitting inside of uh-oh right now. I'm like, oh, okay, this line caused an error. I'm pretty sure cout and endl are correct, but maybe it was star p that was the problem, I think. So I can print, hey, what was p? Oh, that's the 0 address. I can't dereference that. You can even try and print star p. It's like, oh, cannot access that memory. Because we don't own it. Nobody owns the null address. What do you know? So you can even print the values of variables. You can have more variables. It doesn't matter. Like int x equals 42. Let me do that. So to get out of GDB, you can say quit. To exit it, it's like, hey, do you want to stop the program that you're currently running, that I'm currently running? Yes, why? And then you're back on your terminal. You can recompile and rerun it in GDB. So R for run. And now I added this variable. You can print it too. It's like, okay, what's the value of p here? What's the value of x here? It's 42. Oh, it's just beautiful. BT to see where we were. It shows you exactly what went wrong and the line number where it happened and the values of variables around that line. It is the greatest. So that's how you use GDB. And I think you're going to have a lot of fun with it in a future lab. Okay, so definitely take advantage of it and ask me any questions about it. It is a very useful thing to know how to use. All right, so yeah, I think well, hopefully I've convinced you that pointers are useful information to know. And now, my last reason for why to learn pointers, you get to laugh at this joke. Okay, so that is where I want to leave you, and I will see you in the next lecture.